Okay, good evening everyone. Am I audible to everyone? Hello. Am I audible? Okay, I hope all are able to hear me. So, good evening to week 2 of tutorial session or the problem solving session for the course Dynamical System and Control. So, I hope you all have gone through the uploaded recorded lectures for the week 2. So, we will go through few of the important theorems or definitions so that we can solve the problems. So in the last week we have gone through, so for the first week we have discussed the existence and uniqueness of solution for a non-linear differential equation, and the condition for the existence and uniqueness of solution was that f should be continuous for existence, and for uniqueness f should be Lipschitz. Now if we talk about existence and uniqueness of solution for some bounded rectangle where t is bounded and y is bounded, then we saw how to guarantee the uniqueness of solution or the existence of solution for a particular bound of time. So what is the maximum amount of time for which the solution will exist depending upon the bound on the solution of y. So that was given using the Picard's theorem. And in this week, in the second week, that theory have been extended for the linear systems, linear autonomous and non-autonomous systems. So for non-autonomous system of the form x dot equals to atx plus ft, the existence and uniqueness boils down to the fact that if your matrix AT and this function ft are continuous on some bounded interval where t is from a to b, and if the initial time is also lying between that interval where your time t is given, and if there is a eta which is finite, then we say that for this system, for this non-autonomous system, the solution will exist and the solution will be unique, satisfying the initial condition is given by eta, and the solution will exist for the whole interval a to b. Okay, and again this theory has been extended for autonomous system. Now here for autonomous system we have this time varying matrix is nothing but a constant matrix A. Okay, so here everything is very simple. Whether so here our f is equal to ax, so if you found out del f by del x norm, if you take, and if you take any matrix norm A, that is also going to be bounded because A is a constant matrix. So here we say the solution will exist and it will be unique for every initial condition which is in Rn space and for every t which belongs to any real number. Okay, so here we, if a system is not autonomous, then we don't have to bother about whether solution will exist or it will be unique or not, because here the matrix A is constant, so f or del f by del x all are continuous and bounded for all t and for whole of this space. So we say that the solution will always exist and it is unique for autonomous system. Now further we discussed about types of solutions. Okay, so for system of the form x dot equals to a of t into x, we say that since the system is linear, we can find the basis vector for the solution space, and since it is an n dimensional space, so the solution will also be n dimensional, and since the solution is n dimensional, we can expand it using the basis vectors. Okay, and in that way we can also find out the solution for this type of linear non-autonomous system. Okay, and then it was simplified to the solution of the form e to the power at into v, where v is the eigenvector corresponding to the eigenvalue lambda. And then it was derived that if we have n distinct eigenvalues of the matrix A, if A is constant, then the solution will be given by e to the power lambda t into v, where lambda is one of the eigenvalue and v is the corresponding eigenvector. And for n distinct eigenvalues, we have n times of this or n number of these solutions, and then the general solution will be given as linear combination of all these eigenvectors into e to the power lambda t. Now the problem, so when we have n distinct eigenvalues, then everything is fine, but if we have some repeated eigenvalues, then for that we have this these we have to follow these steps to find out the solution. So these steps will be clear in subsequent problems when we solve a few examples. So I will also elaborate on this also. Now in the third case, if we have complex eigenvalues, then what to do? So if we have distinct eigenvalues and those are real, we can find out solution using e to the power lambda t into v. If we have repeated eigenvalues, then we have to follow this step. But if we have complex eigenvalue, then we have to follow the same procedure like we have for real one, and the solution will be given as separately for the real part and the imaginary part. Okay, we will see how to do this when we solve problems. Okay, now for repeated eigenvalues, suppose if we have an eigenvalue given as 2 and it is repeated. For example, we have the eigenvalue as 2 2 2, so repetition is 3 times of the particular eigenvalue 2. So for that particular eigenvalue, we have to find out the we cannot say the eigenvector, but we can say the generalized eigenvector. So for that particular eigenvalue lambda, we have to find an eigenvector v such that a minus lambda I into v is not 0, but a minus lambda I whole square into v is 0. Okay, and these we are doing because we can always expand our this solution matrix as the expansion I plus at plus a square t square, obviously. So like this we can expand our exponential, and using this fact we can find other solutions if we have repeated eigenvalues. So if we have okay, so if we have 2 as repeated eigenvalue, then we have to put a minus 2y into v. We have to find v such that this is not equal to 0, but a minus lambda square whole square v equals to 0. Okay, so this will give us one another solution. And then we have, if that doesn't complete n number of solution or eigenbasis, then we have to proceed further, and then again we have to find a minus lambda I into v not equals to 0, a minus lambda I square into v not equals to 0, but a minus lambda I cube into b equals to 0. Okay, so first will be given as a minus lambda I into v equals to 0. This will give us one solution. Second will be given using this, and third will be given using this. So for we have repetition of 3, so we found out 3 number of solution from here. Okay, and this way we can find out all the solutions of repeated eigenvalues problems. Then there was a concept of fundamental matrix, which was nothing but since we can write our solution xt as some c1 e to the power lambda 1t into v1, let's say v1, plus we can write it as c2 e to the power lambda 2t v2. Suppose this is for a two-dimensional system. Then we can also write it as we can also write it as some sort of matrix. Sorry, what happened? Okay, just give me a few minutes. Okay. Okay. So we can always write the solution in form of some matrix A into constant. So this 8 is nothing but the fundamental matrix solution. And it is formed using the columns and it is formed using the columns of the whose columns denote the solutions of differential equation. Okay, so we stack the solutions as columns, and this form nothing but the fundamental matrix solution, we call it as. And since these are nothing but are formed using the eigenbasis, so these must be linearly independent. So that's why a matrix xt is called a fundamental matrix solution if its column form a set of n linearly independent solution of x dot equals to at into x. Then again we have a lemma about the fundamental matrix solution, which says that for an interval I, a matrix is called a fundamental matrix solution if we check its determinant the solution matrix determinant, if we check at initial time, if it is not equal to 0, then we say that that fundamental matrix is a matrix solution of the differential equation that we are considering, x dot equals to 18 into x. And for autonomous system where a is a constant, in that case the matrix will be called a fundamental matrix solution if we can write that matrix solution where x is our fundamental matrix solution, if we can write it as x dot equals to ax, and if its determinant at initial time is not equal to 0, then we say that this x is a fundamental matrix solution of our differential equation x dot equals to ax. So please remember that here x is a vector, n dimensional vector. Okay, we have x1, x2, x3 up to xn, but this capital X is an n cross n matrix, and it obeys the same differential equation as we have for the autonomous case x dot equals to ax. And since we already have derived solutions using the exponential, so for x dot equals to ax autonomous system, the fundamental matrix solution is nothing but the matrix e to the power at. And these have some properties also. So for autonomous system, the fundamental matrix solution xt, if we have the fundamental matrix solution xt, it need not to be unique, because we can find some another fundamental matrix which is xt into c, and this also will be the fundamental matrix solution. And we can always write the fundamental matrix solution y as xt into c. So any fundamental matrix solution will be of the form xt into some constant non-singular matrix. Okay, so these are the topics that have been covered in week 2, and we will try to solve few problems based on these so that the concepts get clear. Okay, so let's start with today's problems. Okay, so the first problem is related to Picard's theorem. Okay, before starting the problem solving session, are you all able to solve the assignment problems, let's say for week 1, or are you all able to solve the problems?
Personally, I could solve only week one.
Okay.
I mean, assignment one.
Yes, yes, yes. Okay, thank you. So these tutorial session will also help you in solving the assignment problems also, if anyone is facing in solving those questions. So the first question is related to Picard's theorem, where we consider an initial value problem. So we consider an initial value problem for the differential equation x dot equals to 2y square, and the initial condition is given as 2. The question asked about the existence of the solution on the interval. So you have to find out the interval on which the solution exists. Obviously the solution can exist for a much larger interval, but we have to find out that using Picard's theorem. Sorry. Okay, so give it a try, then we will solve it. So what does Picard's theorem say? It states that first we work on a rectangle. So we define a rectangle so we define a rectangle which is given as, let's call that rectangle as R, a rectangle of ty, where t is bounded, or t is defined in an interval, and also our y is, so we are considering time and solution only inside a rectangle. We are interested in this rectangle R, where t is t minus t naught is bounded by scalar a, and y minus y naught is bounded by scalar b. So we are interested in this rectangle only, where t naught and y naught are the initial time and initial value of the solution. So we focus on this rectangle, and if in this rectangle two conditions are satisfied, first is if f is continuous over this rectangle obviously, and the second is that if del f by del y is continuous. Okay, now since continuity imparts boundedness, then we can always find an f which is bounded by some maximum value m. Then we say that the solution will exist for the interval t naught to alpha, where alpha is given by minimum of a comma b by m. Okay, so this is the statement of Picard's theorem. So we fix a rectangle, where in rectangle t is from a minus t naught to a plus t naught, and y is from b minus y naught to b plus y naught. And in that rectangle, f and partial derivative of f with respect to y are continuous, then we can find the bound of f. And if the bound of f is m, then the solution will exist for the interval t naught to alpha, where alpha is obviously the minimum of these two. Okay, now using this theorem, try to find out the interval for this problem. So first let's write down our differential equation. It is 2y square and initial condition is given as 2. Okay, so in order to apply Picard's theorem, first we have to check the continuity of f and del f by del y. So for f, it is given as, f of y is given as 2y square, and obviously on that rectangle it is continuous, there is no problem. then we can find out del f by del y, which is nothing but 4y. And on that rectangle, this is also continuous. There is no problem. Then we can find the maximum over the rectangle t comma x belong to rectangle. Okay, and f we already know it is 2y square, and we have considered our rectangle as y minus y naught less than equal to b, and y naught it is given as 2, so y minus 2 is less than equal to b, so we can find that y is less than equal to b plus 2. Then what will be the maximum of f on this rectangle? Sorry, this is y, t comma y. We can just put, so f is 2 into y square, we can write 2 into b plus 2 square. Okay, and this is nothing but our m. So as per theorem, our solution will exist for the interval t naught, and t naught here is 0, it is given, so from 0 to alpha, and alpha is minimum of a comma b by m, and m is 2 into b plus 2 whole square. Okay, so how can we maximize this alpha? Alpha will be maximum when these two arguments are equal. Okay, so if we say that this minima gives me a which is equal to b plus 2a square, okay, then what maximum alpha we can generate? So for that we have to maximize this b by 2 into b plus 2 whole square. How can we maximize this? So in order to maximize this, we can call this as some function gb. Okay, and we find derivative of g with respect to b. Okay, del g by del b, we can find what will be the derivative of this function, b divided by 2 into b plus 2 whole square with respect to b. So we can find it using, so we have to find the derivative of this function with respect to b. Okay, so it will be nothing but 4, and let's say b by 2, this will be, okay, and equating that to 0. Now when we solve it, we will get, if we solve it, we will get half of b plus 2 minus b equals to 0. So we can find out b as 2. So at this value, its derivative is 0. Then we have to check whether at b equals to 2 it is a maxima or a minima. So in that case, we again have to find out the double derivative. Sorry, we have to find double derivative, and if it is less than equal to 0, if it is negative, then we say that this will be maxima, and you can check that this value will give you the maxima. So we can put this b equals to 2 value in this. So alpha should be equal to b by 2 b plus 2 whole square, and p is nothing but 2. So 2 into 4 square 16, so it is 1 by 16. So our solution will exist from 0 to 1 by 16. Okay, this is how we can find the interval for the existence and uniqueness of our solution using the bound of our function f. Okay, now similar to this problem we have another question. So the second problem is based on this only. So if you have understood how to solve, you can try this one. So we have to consider again the initial value problem, and here the differential equation is x dash is e to the power minus t plus y e to the power 2y, and the initial condition is 0 at 0. We have to find the existence of solution on the interval. So the solution exists on the interval, we have to find out. So we have to find out this interval. What will be T naught and what will be alpha? Please try it. Okay, first let's verify the conditions so that we can apply the theorem. So first we have to check whether f is continuous or not, where f is nothing but the right hand side. So in this case, f is continuous or not if we are talking about a rectangle, obviously. So our rectangle is t minus t naught less than a and y minus y naught less than b, and here t naught is 0 as given and y naught is also 0. So our rectangle is nothing but t less than a and y less than b. So tell me in this rectangle whether f is continuous or not. So for this problem, f is e to the power minus t plus y into e to the power 2y. So obviously for t less than equal to a, there is no problem. This is an exponential. Y is also bounded for the bounded interval, and exponential also remains bounded for a bounded interval. So this f is continuous. Now what about del f by del y? So if we find del f by del y, it is 2 e to the power minus t e to the power 2y plus e to the power 2y and 2y e to the power 2y, and all these functions are continuous and remains bounded for the bounded interval. So the two conditions are satisfied. Now we can easily find out the bound m for this problem. What will be m for this case? That is maximum of t comma y over the rectangle. The maximum of f for this rectangle we have to find out. So it is nothing but since exponential is a decaying one, so exponential will be maximum at the initial time. So since t equals to 0, this term will be 1, and y is maximum when y equals to b, let's say, and this e to the power 2y will be maximum at y equals to b, so it is also 2b. So this is the value of m. Now we have to find out alpha. Okay, so we have m, then we have to find out alpha, which is given as minimum of a comma b by m. Okay, and b is, sorry, m is 1 plus b e to the power 2b. Again we have to maximize this function b divided by 1 plus b into e to the power 2b with respect to b, and for that b we can find out alpha, and then we say that the solution will exist for the interval from 0 to alpha. Now in order to maximize, again we can solve the condition. So we have to say that a equals to b, so that we can find the maximum interval. And if we say that this is gb, we have to solve for g dash b equal to 0, and then again we have to check whether it is greater than 0 or less than 0 for that b. Now if we solve this one, we will get function something like 1 plus b and then we have to solve it for 0. This will give us 1 plus b minus b 2b plus 3 equals to 0. Now if we solve it, we will get b as root 3 minus 1 by 2, and for this value this fraction is maximum. Now we can put this b over here, and we will get alpha as root 3 minus 1 divided by root 3 plus 1. You can check it. Okay, so the maximum interval for which the solution will occur is from t naught, which is 0, and alpha, which is root 3 minus 1 root 3 plus 1 e to the power root 3 minus 1. Okay, so this is how we can find the interval for the existence of solution for a differential equation using the Picard's theorem. If the right hand side is continuous and its partial derivative with respect to y is also continuous, then we can always find the interval for the existence of the solution. Okay, so this covers the Picard's theorem or the existence theorem. Then now move on to another problem. Okay, what else we can have? Yes. Now let's move on to the solution for linear autonomous system. Okay, and then we will solve for different types of solution when we have real and distinct eigenvalues, when we have complex eigenvalues, or when we have repeated eigenvalues. So in the yes,
So what was the answer in the last question?
this is the answer.
Okay, so we found the maximum B when G is maximum, and
Yes,
then that was
first we found out what is M. Okay, then we enforce the theorem which says that the solution will exist for the interval 0 to alpha, where alpha is given by minimum of a comma b by m. Okay, now we have to maximize this interval. How we can maximize? If this minimum will have the argument such that both of these are equal. Okay, now since these are equal, we have to again maximize it with respect to b, or we can say for what value of p this function is maximum, so that we will get the maximum alpha, which is nothing but the maximum interval of existence of solution. Then we say that this, let's call this function as g. Then we find its derivative, which is given over here, and equals it to 0, obviously, to find uh, or is it is nothing but the necessary condition for maxima or minima when we find out. So we find out its derivative with respect to b, equals it to 0, and then solved for b. So we will get b as root 3 minus 1 plus by 2. Another b we will also get as minus root 3 minus 1 by 2. And we can check that for this b, this function is maximum. Then we put this value of b in this one. Okay, because this is our alpha. So when we put b over here, we get root 3 minus 1 divided by root 3 plus 1 e to the power root 3 minus 1. So
understood.
this is
Thank
nothing
you.
but alpha. Yes. Okay, now let's move on to another problem on the types of solutions, or how to find the solutions for linear autonomous systems. And when I say linear autonomous system, you must know that it is given by differential equation of the form x dot equals to ax, where a is a constant. It is a constant n by n matrix. Okay, so such system we call it as a linear autonomous system. And now we will see how we can find out the solutions for this type of differential equation, or for this type of systems. So let's consider first problem where we have okay. So let me write the a. Okay, so for this system, we have to find out the generalized form of solution. For that, we must identify the eigenvalues for the matrix A. Then based on the nature of the eigenvalues, we will proceed further in order to find out the solution. So first identify the solution. First identify the eigenvalues for this matrix A by solving determinant of eigenvalues. We can find find out by solving a minus lambda I equals to 0, determinant. So tell me, what are the eigenvalues for this matrix?
-1, 1, -2.
Yes, that's correct. So let's see. So for this problem, we have three eigenvalues which are given as -1, 1, and -2. So whether these eigenvalues are distinct or not, these are distinct eigenvalues. So we can proceed by just solving for the eigenvectors corresponding to these eigenvalues. So how to find out the eigenvectors for a particular eigenvalue? We have to solve a minus. So let's solve for lambda 1 equals to -1. Let's solve first. So we have to solve a minus lambda 1 I into v equals to 0. Okay, where v is nothing but, let's say v is v1, v2, v3. Okay, so since this is a three-dimensional system, so obviously we will have uh, three sets of linearly independent solution which are going to expand, or uh, what we can say, which are going to form the basis for the solution space for this system. Okay, so for lambda 1 equals to -1, what will be the eigenvector? So we have to put lambda 1 equals to -1 and find out a minus lambda 1 I. So it will be nothing but, here we can put lambda equals to -1. So it is 0, 1, 0, 0, 2, 0, 0, 0, and this will be -1. And v is v1, v2, v3, and this 0 means individual rows are 0. And now we can expand. If we expand, the first one will give us v2 equals to 0, second will give us again v2, 2v2 equals to 0, and third, by solving, we'll get v3 equals to 0. So v2 and v3 are 0, and v1 has no condition. So one uh, eigenvector we can always have the form of 1, 0, 0, because v2 and v3 are 0 and v1 can be anything. Now if we have this as eigenvector for the eigenvalue -1, what will be the one solution eigenbasis? It will be given as, let's say, as x1t. It will be given as e to the power lambda 1t into v. Okay, and it is nothing but lambda 1 is -1, so it is e to the power minus t 1, 0, 0. Okay, similarly we can find out for lambda 2. So let's solve for lambda 2. Lambda 2 is 1. a minus lambda 2I into v, we have to solve for 0, and this will be given as, we have to put 1, it will be minus 2, 0 and minus 3. Okay. So what will be the eigenvector for this one? If we solve, we will get minus 2v1 plus v2 as 0. Second equation will give us nothing, and third will give us minus 3v3 equals to 0. So v3, what we can conclude? v3 as 0. If we fix v2 as 1, then v1 will be, or let's fix, it will be convenient to fix v1 as 1, then v2 will be 2v1, so v2 will be 2. So this is the eigenvector for this case. Then what will be the corresponding solution? x2t, if we find out, it is e to the power lambda 2t. Eigenvector is 1 2 0. Okay, lambda 2t is 1, so it is just e to the power t. Okay, now similarly for the third eigenvector, it was, what was that, minus 2. Again we can find, so what will be the third eigenvector? So this will be the solution. Okay, for this one, v1 plus v2 is 0, 3v2 is 0, and third will give us nothing. So v2 is 0. Now since v2 is 0, v1 is also 0, and v3 can be anything, so it will be 0 0 1. So the third solution will be e to the power minus 2t 0 0 1. Okay, so the generalized solution for this differential equation will be given as linear combination of these three bases of solution space. So the basis of solution space are, the first one is this, second one is this, and third one is this. Okay, and we have to find out the linear combination. So C1 of first one is e to the power minus t 100, C2 into e to the power t 120, and C3 of e to the power minus 2t 001. We can also lump these to write it as C1 e to the power minus t plus C2 e to the power t. Okay, and then 2C2 e to the power t, and then third is C3 e to the minus 2t. Okay, the above can be also written as this as column vector. So this is the generalized solution for the above differential equation. case. Okay, and for this problem, if any initial condition is given, suppose it was given that x of 0 was something like 1 0 1, then we can solve for c1 c2 and c3 for this initial condition, and then we can get the unique solution for this particular initial condition. Okay, so this is how we can solve this for the solution of linear autonomous system. And in this case we had three distinct eigenvalues, so the things were quite simple. Okay, now let's move on to another problem. Okay, consider the initial value problem just given as um, okay, so consider the initial value problem dx1 by dt given as x1 and dx2 by dt which is given as minus x1. The initial condition is x1 0 as 1 and x2 0 is given as 1 by 4. Find out the solution for obviously x1 and x2, x1t and x2t. So we have a second order differential equation which is obviously not linear because the second variable x2 is evolving using a non-linear term minus x1 square, so obviously it is not a linear system, but we have to solve for this solution given that the initial condition for x1 and x2 is 1 and 1 by 4. How we can solve for the solution of this problem? Because here there is no matrix A for which we can find out the eigenvalues and eigenvectors. Here there is no such matrix.
Can we apply variable separable method?
Yes, if we carefully see the equations, so we can clearly see that these equations are decoupled. Means in this one, or not decoupled, but we can see that for the first one there is no term involving variable x2. Okay, so this system or this differential equation is independent of x2. Okay, and since this differential equation is independent of x2, we can also see that this is also linear with respect to x1. Now since it is linear, we can always find its solution using the concept of eigenvalue and eigenvector. So what is the matrix? If we write it as linear system, what is the matrix? There is no matrix, but it is just some constant 1 into x1. Okay, then for this type of differential equation, what is the solution? x1t, it is nothing but e to the power, this is 1, so e to the power t into x1 0. Okay, So this is how we write the solution of a scalar linear differential equation. Okay, and initial condition for x1 is nothing but 1. So x1t we can solve as e to the power t. Now since we have the solution for x1, can we find out for x2? Because this is exponential now. So now try to solve for the solution of x2. Now if we see x2 differential equation, it is dx2 by dt equals to minus x1 square. Now x1 we have solved as e to the power t, so it is e to the power t whole square, or e to the power 2t we can write. Okay, now we can easily solve it. We have to just integrate this exponential in order to find out the solution x2. So dx2 we can solve from, we can integrate, and again this function we can integrate. Okay, so x2 will be given by integration of this will be e to the power 2t by 2 plus integration constant, and this c we can find using the initial value. So at t equals to 0, x2 is 1 by 4. So x2 is 1 by 4 at t equals to 0. Then c will be nothing but 1 by 4 plus 1 by 2, which is equal to 3 by 4. So x2 has the solution e to the power 2t by 2 plus 3 by 4. Okay, so the solution for x1 and x2 we can write as e to the power t minus e to the power 2t by 2 plus 3 by 4. So this is the solution for the given differential equation. So although the system was non-linear, but since there was no influence of x2 on the dynamics of x1 and it was linear, so we found out for, we solved for x1, and then after solving for x1, since the solution is exponential, we can always integrate it to find the solution for x2. Okay, let's move further. So consider the system, or consider an initial value problem where we have the differential equation dx1 by dt given as 2x1 plus x2, and dx2 by dt is given as x2, and we are given the initial conditions also. So we have to find the generalized solution for x1 and x2t. Find the solution. Okay. So let's again write the system. So x1 dot is 2x1 plus x2 and x2 dot is x2 dot is x2. Okay, how can we solve it? So this is obviously a linear autonomous system. So we can find the matrix A for this one. So the matrix A is given as, what is the matrix A for this problem?
2 1 and in second row 0 1.
Yes. So it is 2 1 0 1. Then we can find the eigenvalues lambda 1 and lambda 2. What are they?
2 comma 1.
So yes, it is 2 comma 1. We can solve it by finding out the determinant of this one. By solving this, we can find out one lambda as 2, another lambda as 1. Okay. Now again, we can find the eigenvector corresponding to lambda 1 as 2, and then we can find another eigenvector as for lambda 2 equals to 1. So for lambda 1 equals to 2, we can find the eigenvector by solving this, which is nothing but 0 1 0 minus 1 v1 v2 equals to 0 0. If we solve, we will get v2 as 0. So one set of basis vector will be 1 0 because v1 is independent, so it is 1 0. Now similarly for lambda 2 equals to 1, we can solve a minus lambda 2i again into v equals to 0. So it will be, let's see, if we put 1, it will be 1 1 0 and 0, v1 v2 as 0 0. Okay. And this will give us v1 plus v2 as 0. So if we fix v2 as 1, v1 will be minus 1, or vice versa, anything we can take. Now the solution corresponding to this one, if we say x1 t, it will be e to the power 2t into 1 0, and for this one x2 t, it will be, the eigenvalue was 1, so it is e to the power t minus 1 1. So the solution, generalized solution for xt, it will be linear combination, so it is c1 1 0 plus c2 minus 1 1, or we can write it as c1 e to the power 2t plus c2 or minus, and it is c2 e to the power t. Okay, so this is x1t and this is x2t. But here we have to solve the initial value problem. So the initial condition for x1 is 2 and for x2 is 1. These will help us to find out the constants c1 and c2. So let's solve for initial condition. So x1 is 2 at t equals to 0 and x2 is 1. So it will give us c1 minus c2 and it will give us c2. So c2 is 1 and c1 is 2 plus c2, which is 3. Okay, so finally the solution is x of t is equal to e to the power 3 e to the power 2t minus et and e to the power 2t, corresponding to the initial value 2 comma 1. So it was at t equals to 0. Okay, so here is one simple problem. We have to find out the matrix representation for this differential equation. So find out the matrix representation for d3y by dtq plus 2 d2y by dt square minus y equals to 0, where we have to fix the variable x1 as y, x2 as dy by dt, and x3 as d2y by dt square. We have to find out x dot equals to ax, and we have to find out the matrix A, where this x is x1, x2, x3. Okay, so this is a third order differential equation. So number of variables needed to find out to convert it into scalar differential equations will be 3. So we have to convert this into first order differential equations with the variables x1, x2 and x3. Okay, so are you able to solve it, or I have to solve it?
Ma'am, I have solved, but please you also solve that we can verify our result.
Okay, okay. Okay, so since we have already fixed our variables, the first variable is x1, which is nothing but y, okay, and the second variable x2 is dy by dt. Okay, now dy by dt is nothing but dx1 by dt, because y is x1, so it is nothing but x1 dot, right? So we can write x1 dot as x2. Okay, now what we can write for x2 dot? So let's find out x2 dot. So x2 dot will be nothing but x1 double dot, and x1 double dot is nothing but d2y by dt square, double derivative, and it is given by variable x3. Okay, so x2 dot is x3. Now what about x3 dot if we have to find? Since x3 is d2y by dt square, so x3 dot will be the third derivative of this one. Okay, and d3y by dtq is given as minus 2 d2y by dt square plus y, and d2y by dt square we already know it is x3. so it is 2x3, and y is nothing but x1, so it is plus x1. So we have find out x1 dot as x2, x2 dot as x3, and x3 dot as 2 x3 plus x1. Now we can convert it into matrix representation as x1 dot x2 dot x3 dot, we can write it as some matrix into x1 x2 x3, and matrix entries we can find using these three equations. So the first row will be 0 1 0 because we have only x2, third row will be 0 0 1 because we have only x3, and third row will be, for x1 we have coefficient 1, for x2 we have no 0, so it is 0, for x3 we have coefficient 2. Okay, so this will be the matrix representation for the above problem. Okay, so here actually we have 2 d2 y by dt square, so when we take this to right hand side it will be minus, so I forgotten that minus. Okay, so it will be minus 2x3. Okay, so this is how we can convert any higher derivative differential equation, nth order differential equation, to n number of first order differential equations. So here third order differential equation is converted into 3 sets of first order differential equations. Okay, now let's move further. Let's solve 2 more problems for today. Yeah, we can solve 2 more problems. Okay, let's see how we can find solutions when we have repeated eigenvalues. Okay, so for that we have to find the general solution of differential equation which is given as x dot equals to ax, where a is equal to 2 1 3 0 2 minus 1, and this is equal to 0 0 2. Okay, sorry. So for this matrix we have to find out the general solution. So first we need to find the eigenvalues. Okay, so let's solve for determinant of a minus lambda I equals to 0. Okay, so it will be and now when you solve it you will get, obviously you can see that it will be nothing but 2 minus lambda cube equals to 0. So lambda equals to 2 comma 2 comma 2. So we have eigenvalue 2 with multiplicity of 3. Okay, so what will be the first set of solution basis, so that we can find by finding out the corresponding eigenvector for 2. Okay, and we can use those steps which is there in the recorded lectures when we have when we have arithmetic mean greater than equal to geometric mean. So here it is nothing but we have multiplicity of 3, so 3 is obviously greater than equal to, we will see how many eigenvectors we can find for this 2. Okay, so first let's solve for a minus 2i, because lambda equals to 2 into v equals to 0. So let's see what eigenvector we will get. It is if we put it 2, so it is 0 1 3 0 0 minus 1 0 0 0, and it is v1 v2 v3. So first will give us v2 plus 3v3 as 0, and then it will be minus v3 equals to 0, and the last will give us nothing. So we have the only eigenvector we will have will be v3 0. Since v3 is 0, v2 is also 0, and v1 is independent, so v1 is this. Okay, so this is the only linearly independent eigenvector for this eigenvalue 2. Okay, so geometrically we have only one eigenvectors. Now we have to find out 3 minus 1, or we have to find out 2 other solution bases for this problem. How we can find those? So the first one, since we have one eigenvector, so using this we can find the one solution, which is nothing but like we have done earlier. It is e to the power lambda 1t into v, which is e to the power 2t 100. Okay, so this is the first solution basis. Now how can we find out the other two? In order to find out the other two solution bases, what we will use the fact that since we can always expand this as I plus at plus a square t square by factorial 2 as an infinite series, and we can also, it was proved in the recorded lecture that we can write it as e to the power lambda t e to the power a minus lambda I t. Okay, we can write this as this also. And now since this is fixed for lambda, we can again expand this, and its expansion will be nothing but a minus lambda I plus a minus lambda I plus a minus lambda I square t square by factorial 2, and so on. Okay, so the first solution is nothing but e to the power lambda t into I, and obviously v is the eigenbasis. So the first set we have find out, which is e to the power lambda t multiplied by I into v. Okay, which will give us this. Another, how we can find, since we have expanded this one using this, another we can find out as a minus lambda I into v. Okay, by solving this one. So another will be e to the power lambda t a minus lambda I into v. And obviously by solving this one, and third we can solve using e to the power lambda t a minus lambda I square by factorial t square. Obviously these eigenvectors will be different, so in this way we can find the another other solution. And also for this one we consider all other are 0. For this v3 all others are 0. We have to ensure. Okay, so these three will form the solution basis for this problem. Any confusion, anyone? So the
No,
challenge
ma'am.
is to find these generalized eigenvectors such that this term is not 0, but all the subsequent terms with this v2, subsequent terms means these powers will be 0 when multiplied with v2. And then we have to find the eigenvector v3 such that when multiplied by this is non-zero, but all the subsequent will be 0. We have to ensure. So how to find such eigenvectors? So let's see. So the first one we have already considered. So for the second one we have to solve for a minus lambda I. So the first one we have solved using a minus lambda I into v equals to 0. Second we have to solve for a minus lambda I square into v equals to 0. Okay, so first let's solve for a minus lambda is 2. So it will be 0 1 3 0 0 minus 1. So 0 1 3 0 0 minus 1 0 0 0. So we have to square it and we have to find an eigenvector such that this gives us 0 0 0. Okay, and in order to see that all the subsequent terms are 0 for the particular eigenvector, we can ensure just that this before term is 0 for v2, because when we write a minus lambda I square by factorial 2 into a minus lambda I, and suppose this is 0, then a minus lambda I cube will also be 0. Okay, so we need not to check for all the infinite series, we can just check for the previous one, because that will ensure that all the other terms will be 0 for that particular eigenvector. Okay, so now since we have solved for this one by solving for a minus lambda I into v1 equals to 0, second will be given as a minus lambda I square into v equals to 0. So we need to square this. So I have already calculated the square. It is 0 0 minus 1 0 0 0 0 0 0. Okay, so what it will be, it will give us only minus v3 equals to 0. So we have v3 equals to 0 and v1 was already 100. So we can take it as, since v1 and v2 are independent, we can choose any value, and since already v1 equals to 1 we have considered, so we can take it as 0 1 0. Okay, with this v3 we have to ensure that a minus lambda I into this v, let's call it as
Ma'am,
v2.
I have a confusion.
Yes, yes.
Ma'am, we have taken B3 is equals to 0,
Mm-hmm.
and you are saying that we have a option to choose anything for B1 and B2.
Yes,
Can we
yes.
choose 1 comma 1, 1 and 1?
Yes, we can choose 1 comma 1. Yes,
Okay, okay, thank you.
and it should be such that this I am explaining this v2. So let me give it a different color. Okay, suppose this vector was v1. Okay, and this is v2 corresponding to this one. We have to ensure that a minus lambda I is Yeah, is not equal to 0. Just a second. Yes, this should be the solution for this a minus lambda I into square only. So for this one, the corresponding eigenvector we have found out as 0 1 0. Now what will be the solution? How we can write out the solution? We already have seen that the solution will be written as, the solution is written as x2t. If we see, if we say it is e to the power at 0 1 0, okay, and e to the power at we have written, we can write it as e to the power lambda t a minus lambda I into t 0 1 0, and we have expanded, since lambda is 2, so it is 2t. We have expanded it as I plus a minus 2I into t 0 1 0, okay, because all the other terms will be 0 in the expansion we have just seen, because since a minus lambda I square is 0, cube will be 0, to the power 4 and so on, all terms will be 0. So the only terms that we will have is I and a minus 2I into t in the expansion of this exponential, okay.
Okay.
So what will be the second solution? Let's solve it. It is 1 1 1 0 0 0 1 0 0 0 1, and a minus 2I, it is this matrix 0 1 3 0 0 minus 1 1 3 0 0 minus 1 and 0 into t. So we can do the multiplication and everything, and the solution that we will get will be e to the power 2t t10, okay, after all the matrix and vector multiplication. Similarly, what will be the third solution basis? Again, we can write the solution as the form of e to the power at into v. Again, doing everything, we have to find e to the power lambda t I plus, since we are expanding it as a minus lambda it into v, so this expansion will be a minus lambda it. So up to this two terms we have calculated, so we have to find the solution for this square, okay, by considering that all the further terms are 0, okay. So we have to find v such that this term is non-zero and this term is non-zero, okay. We have to find v such that this term is non-zero and this term is non-zero, and a minus lambda I cube into v is 0, okay. So if this is 0, then all the further terms, power of 3 4 5 6 and to infinity, will be 0. What we will left with? Only these three terms, and this will give us the another solution basis. So for that we have to solve for a minus lambda I cube into v equals to 0. Okay, so let's find first the cube of a minus lambda I. So when we find its cube, it will be 0 0 0 0 0 0 0 0 0. Okay, and let's say the eigenvector is v1 v2 v3, and we have to ensure that this is 0. So what will be the possible choice? We have to choose such that these two terms are non-zero. These two terms means we have to ensure that we have to choose this v such that a minus lambda I into v is non-zero and a minus lambda I square v is non-zero. So when we solve this, we can easily say that all these v1 v2 and v3 are independent. Okay, any choice of v1 v2 and v3 we can make, because this is a zero matrix, and we have to make a choice of v1 v2 and v3 such that this is not 0 and this is not 0. So obviously we cannot choose this eigenvector and the previous one. What was that? This eigenvector, because if we choose this eigenvector, this will make a minus lambda I into this v as 0, and if we choose this eigenvector, it will make e minus lambda I whole square into v equals to 0. So we have to not choose eigenvector of these, sorry, the first one it was this one. So we cannot choose 1 0 0 and 0 1 0 as the eigenvector for the third case. So what is one independent vector we can make? So we have 0 1 0 and we have 1 0 0 we cannot choose. So but we can choose v1 v2 v3 as 0 0 1. Can we choose this one?
Yes, ma'am.
Yes, we can choose this one because this will make both of these two as non-zero. Okay, now since we have the third eigenvector, we can again solve this. We have to solve this. So x3t is e to the power lambda t. It is, sorry, it is I plus a minus lambda I plus a minus lambda I square t square into v. So when you solve it, you will get, sorry, we have factorial t, factorial 2, you will get e to the power 2t, and it will be 3t minus t square by 2 minus t and 1. Okay, so this will be the third solution. So the generalized solution, we can combine these three as their linear combination. So it will be c1 of x1t, c2 of x2t, and c3 of x3t. So you can write, so x1 was e to the power 2t 100, and x2 was e to the power 2t t10, and c3 x3 was 3t minus 2 square by 2 minus t. Obviously you can lump these to find in the form of one column vector only. Let me write that. It is c1 e to the power 2t, c2t e to the power 2t, So this is the generalized solution for this problem. So